We've talked about one theory before. We've talked about Vesper's theory. And remember, Vesper means valence, shell, electron, pair, repulsion. And this has to do with molecular geometry. When we draw a compound, the lone pair electrons want more space for themselves, so they push all the other bonds away from them. When we were doing electronic geometry, molecular geometry, and drawing Lewis dot structures, we're following Vesper's theory. Now we're going to talk about the second type of theory, atomic theory, or molecular orbital theory. Now we're going to say in the molecular orbital theory, electrons are seen as being delocalized, or spread out over a molecule instead of concentrated in a covalent bond. So let's say we have a compound, hydrogen connected to Cl. They're forming a covalent bond with each other. And realize that when it comes to a covalent bond, we have to see it as this. We have two forces basically fighting against each other. We're going to have a bonding orbital is the region of high electron density between nuclei where a bond forms. So the bond that we're forming is forming because we have bonding orbitals connecting together. And we're going to say opposed to that, fighting against the bonding orbital, is the anti-bonding orbital. And this is the region of zero electron density between the nuclei where a bond cannot form. So what this means is that every time we're forming a covalent bond between nonmetals, there are forces that want to keep the bond together, and at the same time there are forces that exist that want nothing but to destroy that bond. These two bonding forces are basically fighting against one another. If bonding forces are greater, the bond forms. If anti-bonding forces are greater, the bond doesn't form. If they're equal, the bond doesn't form. We want the bonding forces to always be greater so that a bond can be made. And how do we determine who's greater? The way we determine is by using these. And these are our molecular orbital diagrams. And I know it sucks, it looks crazy, but you have to memorize them. It's similar to the electron configuration that we learned earlier, except now we're doing molecular orbital electron configurations. But if you remember how to do electron configuration, this is very similar to it. Now, we're going to say the MO on the left side has atomic orbitals and molecular orbitals. The part that we're really concerned with are the molecular orbitals right here. These atomic orbitals on the left and the right to it, those come from the electron configurations which we used earlier. But it's the central parts of each of these MO diagrams that we're concerned with. And here's the thing, we're going to say the one on the left deals with hydrogen H2 to N2 on the periodic table. So hydrogen all the way to nitrogen deals with the one on the left. The one on the right deals with O2, F2, and Ne2. So basically for these molecular orbital diagrams, we're dealing with diatomic molecules. Now remember, we know that there's only certain types of elements that can be diatomic molecules. Have no fear of ice cold beer. That's the sentence we learned to remember the diatomic molecules. But here's the thing. When we're doing MO theory, we're going to treat all these elements, whether they're diatomic or not. Because neon normally isn't diatomic. But for the molecular orbital diagram, we treat it as though it's diatomic. And this is the way it's going to work. So the way we look at this is, technically we start out with S1s, because electron configuration begins with 1s. But here this molecular orbital diagram shows us 2s as the beginning. This S here means sigma. So sigma 2s. And here we have a S and with a star. So this is sigma star 2s. When we see a star, that star signifies we have anti-bonding. So a star means anti-bonding. So here the 2s molecular orbital is a bonding orbital, and the sigma 2s molecular orbital is an anti-bonding orbital. We then go up to p2p. This p means pi. So we have a pi 2p molecular bonding orbital. Then we have a sigma 2p bonding orbital. Then we have a pi star, which means anti-bonding orbitals, and a sigma star 2p anti-bonding orbital. And we're going to do just like we do with electron configuration to solve this.
Thanks for watching. You can find more great exam and study prep videos and channels from Pearson Plus.